Hello, everyone, and welcome to my talk. My name is Ekaterina. I am a senior data scientist at NVIDIA, and in my role as a data scientist, I help our partners and customers utilizing AI technology in the best possible way. And a while ago, I got really fascinated by the topic of synthetic data. I think that synthetic data is a huge enabler and even a door opener to something like artificial general intelligence. So in my today's talk, I will introduce you what does synthetic data mean applied to robotics and perception systems. So let's dive in. And my major motivation to study and to understand synthetic data was robotics. I really like robots, and robots are awesome. Robots come in different shapes and forms, and they can be huge in size, but also tiny robots. They can have different functions. They have different sensors, and they perform different tasks. So there are delivery robots. There are robots who are caregivers. There are robots who fly into space, and even robots performing surgeries. In short, they are great helpers to humankind, and they make our lives better. But sometimes robots fail. So imagine you have a robot which is supposed to come to rescue, and in the end, things like that happen. Or you have a robot and you simply wanted to brew you a nice and fresh cup of coffee, but then things like that happen. Or this is really my favorite one, a ketchup serving robot. What could possibly go wrong? And this one is especially painful for me because it happened in my own place with my vacuum cleaning robot. And the reason why this is happening is that because these robots are being automated, they are not truly autonomous. And the difference between automation and autonomy is that while automated robots, that means that there is a developer behind who sat there, wrote a long list of commands, go straight, turn to the right, and the robot is just blindly following these commands without any capability to act and react on its own. And for a robot, in order to be fully autonomous, we need this robot to rely on AI. We need this robot to be powered by AI. Only powered by AI, a robot could act and react on its own in many different environments. So what do actually AI robots need? AI robots have many needs. And first of all, AI robots need data. Data is the fuel of the digital world. And there's nothing like too much data when it comes to training robots and perception systems. The second need is training. Training means this respective infrastructure, but also the correct algorithms to train your robots. And robots also need testing. Once you've trained your autonomous robot, you need to make sure that it actually works well in all kinds of environments it's designed to work in. So building an AI-driven robot is a hard task. And let's focus today on the data. So data, the typical way to train deep learning models for many years was to go outside, collect some real data, like record photographs, take videos, and then you would label this data and you will train your system. However, working with real data has some limitations. So let's take a look at those. First of all, to train a neural network, you need labels, as I mentioned already. And sometimes labeling data can be really hard. So as in the image on the left, you can see it's a segmentation image. And imagine drawing all these outlines manually. It's a tedious work. And it gets even harder if we work with something like 3D point clouds, working with LiDAR data, another sensor for 3D perception. So it's even impossible to draw these outlines for a human observer. Furthermore, real data can be also hard to human observer, like from different reasons. And these are some images from our own data set, which we use to train autonomous driving vehicles. You can think of autonomous driving vehicles as also robots. And you can see that some images can be dark, blurry, and hazy. They can have some occluded objects, like you don't see this tiny cyclist covered by a car, although he or she is there. Some scenes can be irregular, meaning that you don't even know what to label there. There's some construction on the roads. And some scenes are also very crowded. So you can have too many objects to label, which makes your life as a human labeler is also very hard. Real data is also hard to collect. So one example of such hard to collect data are the so-called long-tail anomalies. By long-tail anomalies, we understand some events which do not happen very often. So let me give you an example. You are an autonomous driving vehicle coming at a crossroad. And your light is green. However, on the right side, you see an emergency vehicle arriving at the same crossroad. And you need to give this emergency vehicle the right to pass, although it's red for this emergency vehicle. So this is a rare situation, but it can happen. And you cannot wait to this situation to happen many times to collect the data to train your autonomous vehicle for this situation, right? So it's hard to get this data. There's also another type of hard to collect data, as I mentioned already, like LiDAR sensor data or radar sensor data. This data is usually represented like point clouds in the computer, and for a human observer, it's not feasible to label it. And some features in the data, they can be indirect. And as a human observer, you don't even see them. You don't know how to perceive them. And these features could be speed or direction of movement. So there is a lot of data which is really hard to collect or even impossible. And also real data has large amortization costs. So applied to factories. In factories, assembly lines get often reconfigured, and then robots needs to adjust accordingly. In the warehouses, robots can change navigation routes, and it means that you can also simply pre-program a robot to follow the same route all the time. And also when we talk about retail, product packaging changes quite often. So think about football games or Christmas. It's often reflected on the product packaging. So yeah, there are many challenges when we work with real data. And the answer here is like how to solve these challenges is by using synthetic data. But let's take a look. What does synthetic data means? By synthetic data, we understand any annotated information that computer simulations or algorithms generate as an alternative to real-world data. In other words, synthetic data is a fake data. Typically, you build some digital twin or some 3D representation of an object, and then you render this representation into some 2D data with according labels, which are programmatically generated together with the representation of the object. Like I'm showing you here on this slide, you see in the lower right corner, you see a digital twin of a warehouse. And on all these different views, you see different kinds of labels. There are depth maps, there are normal maps, there is a semantic segmentation map, there are bounding boxes of different objects. So you can be very creative when we talk about synthetic data. So what are actually the benefits of synthetic data? So now we've learned about the downsides of real data, and synthetic data brings some benefits in order to bridge these gaps of real data. And first of all, synthetic data can provide you with the ground truths which humans can't label. And this can be by treating occlusions. You can easily encode velocity in your synthetic data, depth representation, can also simulate different weather conditions, and think of a bicycle on a poorly lit road in a heavy rain. So you can simulate situations like that. You can also simulate, you can basically extend your synthetic data with programmability. It means that you have the full control over data diversity and distribution. And one example here, those of you who have worked with detection networks, you know the popular the popular benchmark data set called Kitty. And this data set doesn't have too many bicycles in there. So it's kind of biased towards cars and other vehicles, but bicycles are underrepresented. And you could easily fix that with synthetic data by programmatically saying, okay, increase the count of bicycles. That's definitely, programmability of synthetic data is definitely an advantage. Also, speed is another advantage. So with synthetic data, you can iterate faster. You don't need to go outside and collect and label this data. So what you need to do is to prepare your virtual scene, of course, but then you can iterate on that as many times as possible. And you can create as much data as possible in much shorter times. And development can basically start from the day one without the necessity of waiting and collecting and labeling the data. This comes also to a lower cost because, well, if you don't need to spend that much time, then your cost is also lower, of course. And another benefit is accuracy. So when we talk about labeling real data by human observers, we as humans make errors. There are always some small margin where we are not precisely correct with our labeling. However, with synthetic data, it's always 100% perfect. Synthetic data covers corner cases. Think of this ambulance example. You can design all possible rare situations. In other words, you can cover known unknowns. Of course, if a situation has never occurred before and you are not even aware of that, you cannot design in advance for that. But once you are aware of there is a chance of this situation is happening, you can incorporate it into your data set. Another important advantage is that synthetic data has no data restrictions. That means that we can avoid privacy and regulation issues. If you know, like in the countries with GDPR, it's very important to know that the data is compliant, that we, for example, anonymize our data, that we blur faces or license plates. It's also important to make sure that the data cannot link to any particular individuals. And another issue is that some proprietary data sets come with some license limitations. And with synthetic data, which is proprietary yours, you don't have to go through all these limitations. So how does deep learning with synthetic data work? To understand that, let's first look at the classical deep learning process. So here's an example of a typical classical deep learning with real data. Let's say you want to create a cat detector. You collect a data set with many cat images. Your human annotator draws bounding boxes around these cats. Then you convert these images into the format acceptable by neural network, and then you run your training. And when the training is finished, you evaluate your model and you see if the model is performing well, then you're happy and you use your model. If it's not performing well, you tweak your hyperparameters. And sometimes you observe that you need more data. So you go outside again, you collect more data, you label it, and then you run an additional training. With synthetic data is a little bit different. So first of all, we need to start with the content. We need to identify what shall be our content, what are we actually designing there. Once you have understood what you're designing there, you need to synthesize your context. So you need to bring your digital assets into your virtual world. And you also need to randomize these assets. And I'll explain you in a bit why do we need this randomization. Once you have applied all these randomizations, we need to render your scene in 2D. And then you will have your synthetic data set, which you will use to train your model, which you will evaluate again. And the cool thing here is that once you have evaluated your model, and if you see that your data set is underperforming, but for that you need to fix your hyperparameters, you can actually use this feedback loop to tweak the parameters of your rendering system and to adjust your data set creation process. So it's a nice idea which you can use to automate the process of creation of a data set. One important thing you need to take care of when training with synthetic data is the so-called seam-to-real domain gap. By seam-to-real domain gap, we basically understand differences in synthetic data and the real world, and we can have domain gap, seam-to-real domain gap of two types. The first one is appearance gap, and by appearance gap, we understand pixel level differences to the real sensor output. And it can be also in real data. Like, for example, if you're training an autonomous vehicle to operate in a busy city like New York, you cannot only rely on data collected somewhere in the countryside. So it's also an appearance gap. And then for content gap, we understand differences in diversity, context, and behavior to real data. And let me show you why context actually matters. So imagine you're walking in the street and you see there is a tiger, but then you walk closer and see, nope, not a tiger. And I think the next one does not require any explanation. So you see that the context really matters. One good tool to bridge the domain gap is the so-called technique called domain randomization. In domain randomization, what we do, we basically take our assets and we modify, we change its properties, such as color, lighting, textures, and we try different materials. You can also change the morphological features like scale, rotation, and movement. And there are many ways to utilize domain randomization. The first one is the so-called realistic domain randomization, or minimal. Here you basically take your digital twin and you vary some certain properties like movement of objects, lighting condition, lighting placement. However, the scene is really very natural. The second way is the semi-realistic or moderate domain randomization. Here you use the objects which are normal, natural. However, you try to apply different textures which are unusual colors, some funky textures. And like in this image in the middle, you see that there is a room, but it's maybe some crazy person living there, but it's still a room. And you can also have the unrealistic or highly diverse domain randomization, meaning that you bring all kinds of objects, combine them together, and then you try to detect an object of interest there. Why does it work? Is because by doing that, we can encapsulate the real world condition by high diversity in the synthetic data set. So typically, if we have a large representation of possible outcomes, we kind of ensure that the true outcomes are also within this huge field of possibilities. And if you ask me, what is the right way? Which way should I utilize for my data? I would say that there is no one-fits-all solution. You need to see based on your use case. You need to see based on your data. There's another cool example which shows you how domain randomization can help overcoming texture bias. And apparently, the researchers of this paper, or the authors of this paper, have shown that neural networks are actually biased towards texture. In this experiment, they've took the image on the left-hand side, which is the elephant skin, and the network was perfectly capable of detecting that there is an elephant. Then they also put an image of a cat to the ImageNet CNN, and it also returned correct classification. It's a tabby cat with 71% accuracy, which is a little bit lower than the first case. But then they overimposed this image of a cat over the texture of the elephant. The network was still detecting that there is an elephant. And if we would apply domain randomization, let's say if we would change the textures of the cat, like try some funky furs and whatnot, like crocodile skin, then we would be able to enforce the network to be biased towards the shape of the cat. And domain randomization can be also good for testing. So we can actually test our networks in these artificial environments, and we can randomize these artificial environments to test how well our robots can generalize in all possible scenarios. How do we actually bring the reality into the virtual world? There are many different ways, and the first one is the so-called artist-driven manual workflow. Here in this scenario, you basically hire a digital artist, like 3D artist, who will create your objects in like some tools, and then they will bring them with like the textures, and then they will combine them in the beautiful, realistic scenes. Another way is you can rely on traditional photogrammetry. There are some computer vision algorithms like structure from motion, where you go outside, you take images from an object from different sides, from different angles, and then you apply an algorithm by finding some interesting features in these images, matching them together in one image to another, and then apply an algorithm called triangulation to retrieve the geometry of the object. You can also use some point cloud scanning hardware like laser scanners or radars. And then there are different techniques like marching cubes, for example, in order to create meshes from these point clouds. So once you have a dense object, you can build anything with this dense object. There is a very new technique introduced 3 years ago called neural radiance fields. And what it does, it also allows you to reconstruct the world around us using deep learning. So instead of relying on techniques like structure from motion and triangulation, you rely on some neural operators in order to recreate beautiful 3D scenes. And before, it was quite slow to create such a nerve scene. However, my colleagues from NVIDIA research have introduced the method called instant NGP, which is actually open sourced, and you can find it on GitHub. With instant NGP, rendering of or training such a nerve can run with 30 frames per second, which makes it almost real time. And this invention was actually called one of the best inventions of the year 2022, according to Times. So it's a big thing. You can also use techniques called domain adaptation and generative AI. So usually, like with domain adaptation, we understand techniques like transfer learning or image synthesis or style transfer. You can rely on GANs and popular nowadays diffusion models like DALL-E, Stable Diffusion. At NVIDIA, we also have our own Edify. So let me show you this example also. So this is actually my attempt at creating synthetic data with generative AI. And I've seeded my neural network with this very unskillful drawing of a pink panther. I draw it myself, so don't judge it, please. So I took this and then I prompted a neural network with textual prompt, and I've asked it to create me a pink panther, and it turned quite well. But then I thought, no, maybe I can create a cat out of it, and it gave me a cat as well. But then I thought, oh, maybe it's a bear, and it gave me a bear. And then I tried many different things, including a monkey, cow, and even a pig. So yeah, you can imagine I had lots of fun performing this exercise. And to finish my talk, I'd like to introduce the Edify generative AI model, also developed by my colleagues from NVIDIA research. And this generative AI model can create synthetic data of different kinds. It can create high-resolution images based on textual prompts. It can create videos based on textual prompts, and even 3D objects. So it's really powerful. And then you can have this 3D objects or videos. You can extract them from this Edify model, which we host in the service called Picasso. And you can then import these objects into popular editing software, or also to our Omniverse platform, where you can create complex scenes and digital twins of virtual worlds. So the possibilities are really limitless, and I'm looking forward to see what comes next.